Hi class, we're working today on the next section of chapter 1. This is chapter 1.7, modeling with equations. So the focus of what we're going to cover today is how to deal with word problems. So we're going to be going over different methods and different strategies for dealing with them. Typically, along with fractions, word problems are something that students don't like to work with. So word problems are what we also call application problems, right? So generally the answers here will be in some sort of a decimal form. The amount of decimal places that you need are really depend on the problem that you're working with. Generally we use 1 or 2 decimal places when we're solving these kind of problems, right? So if there's decimals in our equations already, then we just use 1 extra decimal place from whatever decimal is given to us already. So if we see no decimal places, then for an application problem, we would put 1 decimal place of accuracy. Okay, so we generally do 1 extra decimal place. So let's talk about some guidelines for modeling. Number 1, we want to read the problem all the way through. Okay, so before we do anything, before we write anything down, before we start to draw any pictures, before we do anything, just read the problem once. Okay. Generally, I will read a word problem at least 3 times during the problem solving process. This includes even what I would call low level problems, right? Like Algebra 1 problems, things that I know how to do very well. I will read them probably 2 to 3 times. If it's a problem that I don't know very well, right? If it's a higher level order problem, like a differential equations problem or linear algebra, I might read that problem 4 or 5 times, right? So I generally will read a problem several times throughout the process. I will definitely read it once without doing any sort of math. I'll read it one more time and I'll start to take notes. And then as I'm solving, I go back through and I read the problem just to make sure I'm doing everything correctly, okay? So it's important to make note of a few things as you read. As you're reading the first time but not actually writing anything down, then the second time you read through it, maybe you will actually take these notes, right? So what is it that we're actually talking about, okay? Are we talking about a problem that requires us to calculate speed? Is it asking for some sort of a time? What's the basic sort of processes that are going on in the background of this question, right? What is important and what is not? Okay, so when you're given a word problem, sometimes you're given a lot of extra information that does not help out the process of solving the problem. Okay, so what I like to call this is sifting through the bullshit to find the gold. All right, there's always a lot of extra nonsense, especially in like a statistics class where everything is a word problem. There's a lot of extra irrelevant information. Okay, so we really want to focus on what's important and what's not important. Okay, what are they asking for, right? Whatever it is that they're asking for, this typically shows up in the last sentence of the problem. This is usually going to be the variable. Okay, so whatever they're asking for, this is generally the variable. Sometimes there's more than one variable, but generally whatever it is that they're asking for is the variable that I'm trying to solve for. Okay, so again, at least one of them. So for 4, how are certain items related to each other? Is there a relationship going on between the 2 variables or 3 variables that are present in the word problem, or the values, right? Are they talking about rectangles? If so, there's going to be a relationship with the rectangle. Maybe I need an equation that has to do with area or perimeter, right? So there should be a relationship that will help me to form an equation between things that are going on. Okay. So again, when I'm doing this first part, I'm thinking of all of this as I read through it. So maybe it takes me 2 times to read through it to really think of all of these things. Maybe I read through it once and I'm just reading the problem, and then I read through it a second time and I'm actually thinking about this stuff as I'm reading it. Okay. And maybe I'm listing this stuff out even. Maybe I'm dissecting the problem and I say, what am I talking about? Boom, this is what I'm talking about. What's important, what's not? This seems important. This doesn't seem as relevant. How are things related? Oh, this is the relationship. This value is 2 less than this value, right? So you can, this number 1 here, read through the problem as many times as you need to in order to kind of make these little small minor notes. Part 2 is draw a picture. Okay, we are, for the most part, visual creatures, right? Back in the day when we were living in the fields and the jungles, right, you use your eyes and your senses to hunt. We pick up on movement, right? That's why our eyes are in the front of our head. We're hunters, right, by nature. So drawing a picture helps us to visualize what's going on, right? So if possible, try your best to draw a picture. Okay, so make sure that your picture is a decent representation of what's actually happening in the problem. Okay, try your best to draw a relevant picture. So number 3, I would read the problem again. Okay, does my picture and my word problem make sense? Is my picture a relevant representation of what's happening? Does everything make sense and agree so far from my picture to my word problem? Next is I want to identify the variable. So again, generally the last sentence in your word problem tells you what your variable is. Not always, but most of the time. Okay, remember that a variable is either an unknown value or it's something that's allowed to change over time. Okay, so lots of time, again, the variable is going to be identified in the last sentence of the word problem. Okay, next we want to try to label things in the picture, as much things as we can, really. And if we have our variable identified, then try to label everything in terms of that variable if possible. Okay, so next I want to read the problem again and make sure that my labels in my picture all make sense with my problem. Okay, so again, does everything agree? Next, I want to try to create expressions and use the relevant information to make formulas, okay, or make equations. So I'm going to look for keywords. That's a big part of word problems. Is a lot of times there are words that have direct translations into mathematics. Like more than means plus, right? Double means you're multiplying times 2. Less than is subtraction, right? So there's keywords that means different mathematical symbols. If you see the word is generally means an equal sign. Okay, is means equals. Per means you're doing a multiplication. Okay, division does happen, but a lot of times it's already implied in the situation that you're working in, right? A lot of times drawing a table will help me to make my equation. Okay, so we'll see that later on. For some instances where drawing a table is very, very helpful, right? So after we have our equation and we try to solve for our unknown variable or variables, the next part is the answer is, do we actually have the question answered? Okay, so a lot of times you solve for your unknown, but then you need to use that unknown in one extra step to actually answer what it is that they asked for. Right, so a lot of times X is the key to the actual answer, but not the answer that you're looking for. So it's very important that you answer the actual question that's being proposed. Lots of times I ask, application problems, word problems, modeling problems, and everyone gets the right X, but they don't get the right answer because they haven't applied the value of X to the situation. Maybe you have to take that X and plug it back into one of these expressions or equations that you found in number 7. So it's always important that you make sure you answer the actual question, because again, maybe that variable is just a smaller piece to the larger answer that you need. Right? Okay. So it's very common that we find the value of the variable we identified, but the variable is not the actual answer to the question, right? But the key to the answer that we want. So there's some common equations that pop up in application problems, especially in the algebra level. Okay, so here we'll have a table of the uses, the actual equation, and the representation that the variables take on, right? So one of the easiest ones are simple interest. So again, you have some money, you're investing it, and you're accruing some sort of simple interest on it. Okay, there's lots of different formulas for interest. We'll see some more in chapter 4. So for simple interest, it's I equals PRT. Here, I is the interest that you earn. P is your principal. Principal means your invested amount. How much are you investing? Okay. R is the percentage rate. It's the amount that you earn on the amount that you invest. Okay. And then T is the time in years that you have this value of P being invested, right? So if I want to invest $100 at an interest rate of 3% for 10 years, I just plug in those values, okay? For the interest rate, it's earning values. So this would be 1.05 if it was a 5% interest rate growth, okay? Mixtures, okay? Everyone hates mixtures, but we'll do some of those. So a mixture is given by C equals X over V, okay? C is the concentration inside of the mixture, right? So if I'm mixing up water and bleach, what's the concentration of bleach inside of the water, right? Or inside of my mixture. X is the amount mixed in, so X would be how much bleach I mixed into the water. V would be my total amount. So V is the total amount of bleach and water mixed together. And so the concentration is the amount of bleach inside of that total amount. Okay, so that's how a mixture works. And that's not only limited to liquids, right? This is also for dry materials. I think a common example is coffee beans, right? If I want to make like a half or a mixture of caffeine and decaf coffee, well, maybe I want 75% caffeinated and 25% decaffeinated, and I need 5 pounds of that. How much of this do I need to add to that in order to have 75% mixture, right? So things like that happen. Okay. Next is distance problems, right? Distance problems take the form of D equals RT. D, if you haven't guessed, stands for distance. R is your rate of travel. What is the speed you're going? And T is the time. How long have you been traveling? Have you been traveling at this speed for years? Probably not, right? Possibly minutes, possibly hours, possibly seconds, depending on what the situation entails, right? Next is area, okay? Area of a this includes squares as well, right? Squares are types of rectangles. Is given by length times width, right? So A is your area, L is the length, W is the width. Then we have things like perimeters as well, which take different forms for different shapes. Area of a triangle is a little bit different than this as well, right? So obviously area really depends on the shape that you're working on. The rate of work is given by A equals T over R. A is the amount of job that you have completed. T is the time that you've been working for, and R is the rate that you've been working at. Okay, so if it takes me, I don't know, let's say 30 minutes to paint a door, and I've been working for 15 minutes, well, then that means that the amount of job is 15 over 30, or 1/2. I've done half of the door, right? So that's the way that this works. Okay. So let's go ahead and do some examples. And then that's pretty much it, right? So this should be a short video as well. So let's solve the following application problems. Okay. A. 2 cyclists start from the same point and they ride in opposite directions. Okay. One cyclist rides twice as fast as the other. In 3 hours, they are 81 miles apart. Okay. Find the rate of each cyclist. Okay. So I read through the problem one time. I kind of understand what's happening. They're going in different directions. One's twice as fast as the other. After 3 hours, they're 81 miles apart. I need to find the speed of each of these cyclists, right? So right there, I've already read through this thing twice and I haven't even started, right? So at this point, I probably want to draw a picture. Okay. I know they're going in opposite directions. So maybe I draw a point as a starting point, and then I draw an arrow going one direction and an arrow going in the other direction, signifying that they are going in opposite directions. Okay. If I want to start labeling some of these things, right, because I know that that makes sense, right? They're going in opposite directions. I know that they are going to end up being 81 miles apart, right? So that's me doing just a quick label, right? I know that from here to here, right? Because one goes one speed, the other one goes twice as far. I don't know if this is actually twice as long as that one or not, but this one is longer than this one. And from wherever this guy gets to wherever this guy gets to, or girl, right? I'm not being gender neutral. Those people is 81 miles. Okay. Now, I need to find the rate of each cyclist. I know that this person goes a speed of something, and this one is twice that, right? So that's going to help me to label more things, right? So I'm going to say that this is cyclist 1. They go at a rate of X. Cyclist 2 is double that of cyclist 1. So if I want to really label things now, right, I can start to make labels. Okay, I got X, I have 2X, and I have 81. So this is a fairly decent representation of the situation that's going on. So what I can do now is I can start to figure out what's going on. So I know that this person travels at a speed of X, and they've gone travels for 3 hours, and they've traveled for 3 hours, right? So I know that this total distance, right, is a distance of X, and this is a total distance of 2X, right? Whatever this speed is, whatever this distance is, this is twice that distance. Okay, so if I start to make a table, rate, time, distance equals rate times time. So cyclist 1 has a rate of X. They do that distance for a time of 3X. So their distance is 3X. Okay, cyclist 2 has a rate that's 2 times that of cyclist 1, and they also ride their bicycle for 3 hours. So their distance, which is rate times time, is 6X. Okay, so now I've incorporated the 3 hours, right? And I know that this value plus this value has to equal a distance of 81, because this is a distance for cyclist 1, this is the distance for cyclist 2. When I add those together, I get 81. That is my equation. 3x plus 6x equals 81. Okay, where 9x is 81, giving me x equals 9. So x is 9, but what does that mean? Did I answer the question? Not really, right? Because what the hell is 9? 9 doesn't really mean anything. 9 is the rate of cyclist 1. But that would not be my final answer, because that is not the rate of the second cyclist. I need the rates for both. So did I answer the question by finding x equals 9? No, I did not. I answered half of it, but even that I didn't put into any context, right? The answer is that cyclist 1 goes 9 miles per hour and cyclist 2 is 18 miles per hour. That is an answer. X equals 9 is just a number. Okay, so I need to use this to actually finish answering my question. Okay, so for B, we have that an herbal mixture is to be made out of mixtures A and B. Okay. Mixture A contains 20% of a particular herb. Mixture B contains 15% of this same herb. How many pounds of each mixture must be used to create a 5-pound mixture that contains 18% of this herb? Now, I just read this through once. Okay, I tried to hold on to as much as I could, but it makes absolutely no sense to me right now, right? So I'm going to read it one more time and try to break it down, right? So I have an herbal mixture. It's a blend of 2 different things, okay? The first thing has 20% of something of interest. The second one is 15% of that same thing of interest. Okay, so that much I can make sense of. This last sentence, let's break that down a little bit more, right? So the question is, how many pounds of A and how many pounds of B, right? How many pounds of each mixture? So how much of A and how much of B do I need so that in the end I have 5 pounds total, and that this 5 pounds has 18% of this herb that's in both of the mixtures. Okay, so A is already blended, B is already blended, but I need to blend those blends so that I have 5 pounds total and that my blend has an 18% concentration, right? So I just read this 3 times and I haven't even gotten started yet, right? I haven't written anything down on paper. So let's start to draw as much as we can. Let's try to put some stuff down on paper so that it makes sense, right? So I have mixture A. It contains 20%. I have mixture B. It contains 15%. I'm going to mix those together into a new bag that contains 18% mixture, and it weighs 5 pounds. Okay. So let's say that A contributes X pounds into this 5-pound mixture, right? So if I need this to be 5 pounds and I'm throwing in an unknown amount of this, how much do I add in of this then? Well, if the whole thing is 5 and this is, let's say I added in 2 pounds from here, that means I would need 3. How did I do that? Well, 5 minus 3 is, or sorry, 5 minus 2 is 3. So if this has to be 5, this is X, well, what's left over is 5 minus X pounds. Okay, so there, I've drawn a picture with some labels, and then I've made an expression out of the relationship through the situation that was given to me. Okay, so it's going to look something like this, right? I can label this a little bit more thoroughly in this point now. Mixture A is X pounds. Mixture B is 5 minus X pounds, because when I add X to 5 minus X, I end up with 5. All right, so where do I go from here? Well, I kind of hit an impasse. I want to start trying to solve the problem, so let's go ahead and build the table out. Okay, so this is a mixture problem. Well, we know that mixtures, come back up here, follow this, right? Concentration is the amount mixed in over the total amount. So for our case, we know the total amounts are 5. So we can start to throw in how much we're throwing in of the 20% and then 18% to figure out our final concentration, which we know our final concentration needs to be 18, right? So let's start to build an equation. So we have CV and X equals C times V. So that's just me manipulating the equation a little bit because X is the thing that I want to figure out, right? So for mixture A, the concentration is 20%. The volume that I'm mixing in is X, okay? So my quantity that I'm going to be using is 0.2 times X. For mixture B, it's 15%. The volume of B that I'm mixing in is 5 minus X. Multiply those together, the amount of B in the mixture is 15 times 5 minus X, right? And so for mixture C, I know that it's it's 18%, it's 5, and when I multiply those together, I get 0.9, okay? So that means that if I add these together, it needs to equal to 0.9. I could have actually done this a different way, but for me, it was the way that made the most sense in my head. I could have kept it as X equals, C equals X over V, and I could have done this a different way, and I'll still come out with the same thing, all right? But here, I find it's a little bit easier because it looks more like a linear, it is a linear equation that's a little bit easier to solve. There's no fractions going on, right? If I made it the other way, I'd have to deal with fractions, which is fine. I still just clear the denominators out, but here I don't have to worry about them at all. So I'll distribute this 0.15 across, right? Combine these like terms, which gives me 0.05x, and I can subtract this 0.75 to both sides. Or, which is what it looks like I did, is I basically cleared the denominators, okay? Even though there's no denominators here, I found the smallest decimal place, which is the hundreds place, so I multiply everything by 100, okay? If I multiply everything by 100, that means I move this 2 decimal places to 20, this 2 decimal places, this 2 decimals, this 2 decimals. It's just easier than working with decimals because arithmetic on decimals, to me, is equally a pain in the butt as fractions are. So same thing, this gives me 5x, Subtract the 75 gives me 15. That's a lot easier for me to do in my head than the decimals. So x equals 3. Okay. Again, what the hell does that mean? Right? I don't know. So we have to go back and say, well, what is it that I'm actually looking for, right? I want to know how many pounds of each mixture must be used to create a 5-pound mixture that contains 18%. And we let x be the amount in of mixture A that we contribute. So if x is 3, then that means that this is going to be 2. Okay, so now that we have a value of x, we can use that to talk about the actual answer, right? So we use 3 pounds of mix A and 2 pounds of mix B. All right, and so that's it for our application problems. I'll see you guys in the next section, 1.8.